We often associate meditation with perfect stillness, but beneath the skull, the brain remains in a state of high-velocity activity. Focused attention meditation is an iterative cognitive cycle. It is a continuous process of maintaining focus, detecting a lapse, and reorienting the mind to the present moment. This cycle is driven by a competitive dynamic between two functional modes, a task-positive state that processes the external world, and a task-negative state that generates internal thoughts. Because these states share overlapping neural resources, they cannot both operate at full capacity. When the internal state gains metabolic dominance, the mind wanders. Observing how these states alternate provides a map of the functional networks involved in cognitive control. This model represents the brain's large-scale architecture, specifically the 5 core networks that govern how we allocate our attention. The primary task-positive operators are the central executive network and the dorsal attention network. These regions activate when we scan a crowd or solve a complex problem. In opposition is the task-negative operator, the default mode network. This system activates whenever we are not engaged in a specific external task. Managing the transition between these modes are the salience network and the ventral attention network. These act as the system's internal switchboard and circuit breakers. Although these networks are anatomically distributed across different regions, they function as synchronized units. These networks are structurally anti-correlated. Activation in the task-positive systems requires the active suppression of the default mode. The contemplative cycle begins with phase 1, anchoring attention on a specific target, such as the physical sensation of the breath. This requires the dorsal attention network. This system focuses neural resources on specific sensory inputs while filtering out competing distractions. Within the DAN, the frontal eye fields and intraparietal sulcus lock attention onto the breath. The central executive network supports this, using the dorsolateral prefrontal cortex to keep the brain focused. To maintain this state, the brain must continuously suppress internal distractors and irrelevant sensory noise. Keeping these task-positive networks fully engaged requires a high metabolic cost, consuming a measurable portion of the brain's glucose and oxygen. Lapses in attention are a byproduct of this energy demand, occurring whenever the metabolic budget reallocates resources back toward internal states. Eventually, executive fatigue sets in, and the object of focus is lost. The task-positive networks go offline, relinquishing control. The default mode network immediately takes over, rapidly pulsing communication between the medial prefrontal cortex and the posterior cingulate. The medial prefrontal cortex begins generating self-referential narratives and evaluating the personal significance of recent events. Simultaneously, the posterior cingulate and temporal lobes retrieve episodic memories and simulate future scenarios. These outputs integrate into a simulated internal reality. The practitioner is no longer focused on the breath. They are lost in an internal story. When external tasks are removed, the brain's default response is the automatic construction of a narrative self. The mind wanders until phase 3, the moment of awareness when the practitioner notices the lapse. This awareness is generated by the salience network, specifically the anterior insula and dorsal anterior cingulate. The anterior insula detects the internal narrative as a salient error. The salience network then signals the system to suppress the default mode's activity. This leads to phase 4, the shift, the process of re-engaging with the anchor. To break the narrative, the ventral attention network acts as a circuit breaker. This network detaches neural resources from the self-referential story. The central executive network then reallocates those resources to the dorsal attention network, reestablishing focus on the breath. This transition depends on the precise temporal coordination between the salience and ventral attention networks. This cognitive cycle lasts only seconds, but when repeated over thousands of hours, the pathways involved in detecting and shifting attention physically thicken. We measure these changes through resting state functional connectivity, which maps the brain's internal communication while at rest. In a novice brain, the resting state is often characterized by a hyper-dominant default mode network that is largely isolated from the networks responsible for control. This rigid structure correlates with longer, deeper periods of involuntary mind wandering that are harder to interrupt. In contrast, the brain of a long-term meditator shows increased connectivity between the default mode and the salience networks. This suggests the meditator's brain maintains a lower baseline of default mode dominance. Repeatedly activating these circuit breakers remodels the brain's architecture, making cognitive control a structural trait. This increased functional coupling has direct consequences for everyday behavior. An upgraded salience network allows the brain to detect the onset of rumination or emotional hijacking faster. Addressing DMN hyperconnectivity is why these protocols are relevant in treating disorders like depression and ADHD. In these conditions, the brain is stuck in rigid, self-referential loops. Strengthening the connection between the salience and default mode networks disrupts those loops. The byproduct of this plasticity is meta-awareness, the ability to monitor the contents of the mind from a stable perspective. Effective practice refines the networks that regulate the flow of internal thought, ensuring the brain remains responsive to shifts in attention. Through these targeted biological changes, meditation allows the brain to regulate its own default states.